or the basis of range T and extended. Um, All right, so the idea is we want to construct E. Oh, sorry, you said to extend it based upon the image. Did I miss something? Did I miss something?
No.
All right, so I'm going to draw a picture here. So if you're in the null space of, where are we? All right, so if you're in the null space, what's going to happen when you apply T?
It will be 0.
Okay. And then what happens when we apply E? That's a
E0 is
tautological.
0.
Okay. All right, so now if we apply an element of, so now we have this other spot, C. When you apply an element, a basis element here, and you apply T, you're going to get T of Ci. And then we want to apply E. And what do we want out? What needs to be here? If this is equal to S, what needs to happen?
It will be the basis of S.
Well, it's we don't we want this needs to be, sorry, this needs to be this, we need to get out whatever S of E1 is. C1, sorry, that's a C. C. And then we can do, oh, wait, hold on. We need to be more careful, right? Hold on. Let's be more careful. We're gonna back up. We're gonna back up. I'll save these notes later. All right, so note that the, what's this? B uh, um, all right, so this is a basis. So in my picture, well, whoopsies. This right here is a basis, which is all the elements you can get out. Well, it's either all of these or all of these. And that forms a basis of V. So then we can define E if you're in B B U and E of so far so good. Questions so far?
Sorry,
Mm.
but I think V equals naughty, the direction of naughty and range T is not true.
Oh yeah, that's not true. Yeah, that's not true. That is not true. That is not true. Yes. Why did I write that? That is that not true? That is not true. That is not true. That is not true. Okay, so what do we want to say instead? No, that is not true. Okay, so maybe this is problems much harder than it looks.
I think you mean TC is they are linearly independent.
Okay, let's go with that. We're gonna run into a problem somewhere when I think we get finite infinite dimensional, but that's TCI. Okay, I agree with that.
So we can extend it into a basis of V.
All right, so this picture still stands. So basically we have a basis of V. You have all of this stuff right here, and you have something else. This is the extension. And then we're going to define the, okay, and then similarly, we can do the same thing with S, right? Okay, we can move this down here.
I think we might have a problem because the range of S and the range of T might not be the same in that. From what I understand, E times T is we can consider the matrix of S and T, and instead of considering them operators, we can consider them matrices. So E is a linear combination of T, and that means that the image of T of the column vectors of T over E has to be equal to the vectors of S, but that I don't think that can happen if the range of T and the range of S is not equal.
No, okay. Let's continue with this picture. So we have a basis here. And we've extended this one. So we should be able to say, we should be able to construct T by simply taking E of TCI equals SCI. So we're going to just pair whatever vector this is to what it needs to be. And that's what E is going to do. And then over here, we're going to just pair this vector with some arbitrary vector over here. And these should be the same size.
I think this still work for infinite dimensional space.
I agree. So what do we need to do? I guess the question for you is, what do you think needs to be done?
Some lemma that we haven't studied.
Blah, blah, blah. Let's see. I agree. I guess what's wrong with the current proof? Maybe that's the key. The key question I want to perfect your understanding. What's wrong in the infinite dimensional case? What's wrong with the current proof? Or what could be wrong? I guess what it boils down to is this assumes right here. So we're assuming there's a bijection between D and E. And I think that's the missing part. I think that's the missing lemma or assumption. maybe I'll stop there for 23 for now.
Yes.
Okay, so I'll put a big star here. So this, I mean, one thing to take away from this exercise and this course in general is that infinite dimensions and finite dimensions, you know, that's a big leap. It's a big change. And I guess the same proof basically holds for 23b. So 23b is a similar what should we do next?
What about 15C?
15c. 15c.
Well, I want to ask about if there's a proof that doesn't involve matrix multiplication and doesn't use eigenvalues.
So I think this one is just proof by induction.
Well, by induction, you can use matrix multiplication, but I'm curious if there are any other proof.
Is there another proof? I guess the simple proof is understanding what this is. So let's see. What's the simple proof? The simple proof is the simple proof is that image. Okay, so the intention of the intention of this proof is for you to practice doing matrix multiplication. So A times A ij or ik is equal to the sum of A ij ajk. K goes from 1 to n. So this is what the idea is for you to practice. You should practice this notation. And then if I is bigger than j, then sorry, if I is bigger than k minus 1, then either aij equals 0 or ajk equals 0. Wait, that's not right. Right, yeah. Right, and then you can induct on this -1. So this -1, what's happening is when you take an upper triangular matrix or a strictly upper triangular matrix times itself, this is all zeros. You're going to get something that's like this. So maybe the best thing to do is think about this algebraically. Does everyone understand? Is my diagram clear?
Yes.
Yeah. So maybe the easiest way is if you're upper triangular, then you can view this as the range of T restricted to the span of, restricted to the span of EK plus 1 to EK, so EN. Let's write this more clearly. Is going to be contained in the span of EK plus 2 to EN. No, that's not right. Hold on. What am I doing? EK plus 1. Oh, no, okay, hold on. I did this backwards. Hold on. Okay. E1 to EK is within this. So this is what's happening algebraically. Right, so put it into a picture. Right, this first column has to be 0. So this tells us that T restricted to the span of E1 is in fact the range of this is in fact just the 0 vector. And then the next one, I don't know what's here, but it has a bunch of zeros after it. And then together, these two tell us that if you restrict yourselves to the span of the first two columns, then the range of T restricted to the span of E1, E2 is equal to the span of whatever the second column is, which could be 0. But in any case, that's a subset of the span of E1. So if this star is non-zero, then you get E1. Right, so this tells us that inductively that if you take any vector, then when you apply t, if you take any vector, the possibilities of the next one is one dimension less each time. So eventually you're going to get to zero, and the only map that gives you zero for all V as matrix. So that's probably that's the algebraic way of thinking about this, as opposed to doing it with linear algebra. This is an algebraic approach for Is that good? Does that satisfy your
So each apply yeah, each time we apply t, the span gets smaller until
Right.
it reaches zero.
right? And but the key is not just the span. Okay, the span gets smaller, but the key algebraic property is the output of the previous one lies inside the restriction you need to apply for the next one.
Yes.
Like so because that happened, you eventually get to zero. Anything else? I'm here for another hour or more. So
Can you solve the question 24?
24. Is there a specific question or just what about it? What is
When does equality holds?
when does equality hold? That's a good question. So equality will hold rank A. Do we want to go through the proof? Should we go through the proof of this?
Yes. I want to see as many as proof.
Okay, so let's I need letters. Let G, I'm out of letters. Okay, so G be a basis for the image for the range of AB. All right, these are finite dimensional. Hold on, no. Do I want this to be an image? Yeah, okay. So we have we'll do this one first. So we have G1 to GK. Sorry. All right, so notice that K is going to be equal to the rank of AB. We want to consider
I think range AB is the subset of range A.
oh, right. Okay, yeah, okay. Good. Yeah, okay. All right. That's a good way of doing this. All right, so that's the
B, the output of B is not the same as the output of A. It doesn't go to the same set.
but the range of A does go to the same output as the range of AB. Like this is the same map. This has the same codomain. This goes from RK. Sorry.
A goes from RK to RN. AB goes from RK to RN to RM. So AB goes from RK to RM.
Okay, maybe the notation is, maybe I mixed up the notation. This should be the same target space. Yeah, no, hold on. This should be, this is, okay, so I think I mixed up the notation here. This is supposed to be rows by columns. So this is supposed to be N to K. And this is supposed to be rows, sorry, columns. So if you think, okay, so ignoring the notation, ignore the notation. I mean, ignore the order of n and k and whether it's right or not. A has to have the same number. This is, suppose this is S by T, then AB is equal to S by T, and then B has to be T by U. So in the end, A is going to be going to RS in my example, and AB is also going to be going from RU to RS. So the image lives in the same space. So I don't think that's that's not a consideration here. Which has? All right, is this good?
Oh, yes.
And then going backwards. Should we go the other way?
Yes.
Um, all right, so we're going to apply the rank nullity theorem. That okay, B should be coming from Rn. So n minus rank B is equal to the dimension of the null space. And likewise, n minus the rank of AB is equal to the dimension of the null space of AB. All right, then we can apply the same idea. Basis for null B and this necessarily has K must be the dimension of the null space of B. And then since the null space of B is a subset of the is a superset rather, sorry, is a subset of the null space of AB, is it clear why this is true?
Yes, yes, it's obvious.
That's obvious. Okay. All right, and then we're going to apply that this is equal to n minus the rank of B, and this is equal to n minus the rank of AB. Then we get and this applies the rank nullity theorem. Is that any questions about that guy? About this question? I think that's the main takeaway of this problem and many others. All right, so maybe on that note, how does 11 work?
We can just apply the rank nullity theorem.
I don't think does the rank nullity theorem give you all of these?
I guess we have to establish that T and T prime is like similar. As in there's a correlation between the range and null.
Okay, so this is equal to, let's just have T go from n minus okay, this is the rank nullity theorem. What is this? Oh, range, sorry, range. I guess the first question is what's the relationship between these two?
The sum equals n.
These should be equal.
Oh, I confused it with the annihilator.
All right, so these should be equal. No, that's not equal. Sorry, those aren't equal. Okay. Okay, this is equal to m minus okay, but this is equal to m minus the dimension of t. So this is the row rank equals column rank. All right, let's do what does this give you? The annihilator of the null space. question is this, what is this? I guess the question is this obvious? Or this should be the dimension of range of T. Is this obvious? Did I get disconnected?
Not sure.
So this follows from the idea that what is this? T if you take the map, if you apply T, no, let's see. Yeah, okay. We'll call it T star. That goes from V, where you not out by the mole space of T, to W. This is surjective. Sorry, this is injective. So this map is injective. So the idea is if you mod out by the null space or the kernel, then what's left is an injective map. So this guarantees, together with the rank nullity theorem, right, a basis for this one will give you a basis for the image. So this tells you that oh wait, this is more complicated than that. Hold on. Okay. Null T okay, so maybe the best way of doing this is all right, let's just prove this from scratch. Should we do that?
Yes.
Okay, so let's just prove this from scratch. All right, so let and we can extend this of our what's this? Our n All right, so the key point here is that B1, sorry, T of B1 is equal to 0. T of B I is equal to 0 for I less than or equal to K. And T of BI is not equal to 0 for I greater than or equal to K plus 1. Uh, all right, so further, we have that these are linearly independent. Oh, no, not just that. These are linearly independent. So these are image of T. Is that what I want to do here? Okay. Um, all right, and we can extend this to basis of Rn. All right, so altogether we have a basis that looks like this. This is M vectors. So what I want to do. Okay. Where are we? Hold on, I'm stumbling. Any thoughts? Oh, wait, I'm screwing up here. Hold on. This is equal to, that's why we are, this should have a prime on it. Okay. All right. I screwed up. There should be a prime here. Why did no one tell me this? All right, there's a prime here. All right, let's back up. We're going to, oh my gosh. Cut through. All right, there should be a prime here. So maybe in normal speak, this is that the null space of a matrix. And you can think of this one as the perpendicular space. We're going to cover that in chapter 5 is equal to the range or the image. Sorry, this is the dimension of the range of A transpose. Hold on, that's not even that. That's just not even a dimension. These are equal. If they are, no, that should be equal. Wait, so this is not like something. No, that's right. Okay. If all right, let's just do it in this case, and then we will see what we get. Hold on. Wait, what am I doing? Oh, which means okay. All right, so that's the proof for one direction. And then you can apply it the other way. So this is, okay, so this is for if you have, if you view it as a matrix. So if you view it as a finite dimensional matrix, as opposed to an abstract linear map, then you can just apply the you apply the transpose to various things, and you get that anything in your range has to generate something that's orthogonal. So these are in fact equal spaces, not just their dimensions are equal. All right, and these two facts together should give you the relationship between all 8 of these spaces for number 11. Where is this? All right, so these are equal because this is L of t is equal to all right, and we have null of t prime annihilator. It should be equal to the range of t. No, that's right. Yep. All right, so this says that the dimension of the null space of t but these dimensions should be equal. This dimension is equal to the same one as this one. All right, so that hits all 8 of the spaces. Are there other questions, comments? I'll keep going for as long as people want to.
Do you have Axel's book on hand? Because
do.
someone wanted to ask about problem 11 in 3F, I think.
Okay.
Page 104.
I have 3F number 11. I have on 115.
Oh, so I think it's, I don't know if it's 3E or 3D. It's on 104, so.
Okay, that's 3E number 11. Yeah. For A or B? I'm assuming it's B, right?
Yes.
All right, so if um, if so, yeah, if all right, so then we have a basis for um, uh, so I think I think 11B is a diagonalization argument. Um, uh, all right, so we're going to construct a V that is not in the list. Um, take B prime. Um, uh, um, uh, oh, maybe it's as simple as this. Hold on. Um, what's you're going to choose V very cleverly. Choose V. I guess the best thing to do is to do this. Yeah, okay, so we're going to choose V very cleverly. Choose V to be um, um, there's- oh, okay, okay. Okay, so this is probably not the best way of doing this. Okay, so if they're only infinitely dimensional, then uh, all right, BI uh, okay. All right. So this is what we're going to do. We're going to say let Sij be equal to the set of coordinates that um, no, that's not what we're going to do. All right. We're going to choose V. Only finitely many K. Okay, sorry. Are there any thoughts? Okay. All right, so this is what we're going to do. We are going to choose the representative. Okay, so we can use, all right, so we're going to choose this guy in a specific manner. Okay. All right, I think it's more straightforward than it looks. All right, so we're going to choose the representative, and we're going to choose B star I, so that the first I minus 1 entries or 0. Okay, so maybe the better way of thinking about this is if it's infinite dimensional, we can choose, maybe it's best just to illustrate this with an example, maybe just do an example. So we're going to take your representatives. We're going to view this as a matrix. You put them in a list. This is going to be infinite. And you're going to cut it off whenever you can row reduce this matrix. So at some point, these vectors have to differ. And so at some point you get you can transform these vectors into a linear combination where each one has a leading 1 in front and there's a 1 in every column. So let's just call these transformed vectors C1 through CK. Then we're going to let W be equal to the sum of alpha I C I. I don't even need this. Just the sum of all these. And this gets cut off at some n. And then you're going to add just a 1 here. Or no, you're going to add, what are you going to add? Yeah, you're going to add a 1. So this vector right here will not be, no, it will be. Hold on. Oh, no, okay. PK. Did you have any specific thoughts on this problem? Let's see. This one. I guess the simplest argument is you're going to take all your representatives. So I think we can do this one better. You can take all your representatives doesn't even have to be infinite. And it doesn't even have to be finite. It can be countable. So it's countable. And then you're going to just change you're going to just change these entries, and then you should be able to loop back at the top. You're just going to augment this entry, say, by +1. +1, do I want to do +1? Oh, okay. Yeah, so maybe that's just what we do. Not even do this, hold on. Um,
Can you send the note after the end of the class?
yeah, of course. I feel compelled to finish this one. I
Well,
budgeted,
I'm sorry, I was a bit distracted.
we're answering your question on 11B. We're
Uh,
on this one.
Yes. What's the idea?
So I think the idea is you apply a diagonalization argument on a finite basis.
Diagonalization as in the matrix, or
Sorry, no, as in Cantor's diagonalization argument,
oh,
right? So you would take like a basis, and then you would you take a finite basis, a finite basis. Let's see. Finite basis, infinite dimensional. Uh, um, There's infinite dimension. All right, so maybe we can apply. Okay, so let's apply this one. All right, so the best one to do is that. Take t to be equal to that's not gonna help. Okay. All right, let's give it one more minute. And then diagonalization. Okay, let's not do that. Um, um, uh, all right, let me think. Let me think about this one. I guess a silly question is if I were to come in tomorrow, would anyone want to meet up?
I think. Do you need an answer like right now because we haven't come to a consensus?
No, I don't need an answer now. If you tell me by noon, I can make something work.
All right. I think we will
I will
answer you by-
I probably will have to go in anyways. So it's not an inconvenience for me at all.
We will respond to you before noon.
Okay. All right. So I mean, I'm happy to keep going here. I don't want to dwell on this question too much. This question is definitely intuitive, and I'm sure there's a clever proof.
I think we can finish it tomorrow.
All right. So let's just work. Yeah. Let's just think about this tomorrow. Is there anything else people want to work on tonight?
I think we don't have any more. So
I mean, I'm happy to keep thinking about this one. I don't want to keep people here. Oh my gosh, that's better.
Can I have a question?
Sure.
So in the exercise number 2, when you ask whether the quotient space V over no T is a vector space, can we prove that using the first isomorphism theorem instead of like verifying the axiom?
Sure. I mean, it's just a trivial exercise, no?
Yeah, but I find verifying all the axioms have too long.
Okay.
So if we want to use the first isomorphism theorem, do we have to like flip it again?
No, that's fine.
Oh, all right.
Let's see.
I think we can finish now.
Yeah,
There's
we can
some-
finish. Do you have a suggestion, or we should just call it? We should just end it.
Yeah, we should. I think we should end it. It's
Okay, we can
kind of
end
late.
it. Okay, yeah,
End
yeah.
it.
We can continue tomorrow.
We'll continue tomorrow. I will think about this question because it's gonna bug me if I don't have it.
Okay, we will send you a response by noon.
By noon. Okay, and I'll be in anyway, so it doesn't have to be everybody. If anyone individually, like if people decide it's not necessary. What was the reaction? Everyone's reacted.
I just misclick. I'm sorry.
So I'm just saying that if people, if the group decides they don't want to meet, but individuals want to meet, I would just encourage you to reach out. I will probably be at the campus at the university tomorrow anyways. So you can let me know.
All right.
All right, let me save this. Share to PDF. Yes. Yeah. Oh, I have to do this. Okay. That is going to be a pain in the butt. Let's try this. Okay, I will make sure the notes get sent out, but I think we should just end it now. So I will see you guys at the worst. I'll see you on Thursday and sorry, Tuesday, and if not, tomorrow.
Goodbye, sir.
All right, goodbye.
Okay, goodbye.
Goodbye.
I'll hang around if people have questions.
Oh, I
Right.
have another suggestion for the exercise in the 11th, but I'm not sure if it's reasonable because I go a different path than you. My idea is to prove that like f infinity over u is a infinite dimensional. It's infinite dimensional. Then I would try to find a list of linearly independent vectors they would um, that they would be dependent on like from u1 to uk, and I would try to prove that they are linear independent for every k. And to construct that, I would try to. It's kind of a long way, but my main idea is that I try to make coordinate of uk as the number 1 in every power of the k prime number and 0 in all other slots, and then I will try, and then I will prove that it's linearly independent. But I think it's a very different path, and I'm not sure if it works.
All right, so let's go back to this one. So you're saying let
UI is a vector that's in f over u, and it's represented by a vector. So it has which has the coordinate in the power of limit in the a power of I prime and
oh okay. Right.
yeah, like that. It's the power of I of the I prime. We have the 0 in points. So like if we try to like find a linear combination of O from UI1 to like UIK, and I try to make it equal to 0, then I would have to show then it's kind of trivial that every scalar has to be 0, or else like there would be infinitely many 1 in prime powers.
So the key thing is you have to show that there is no list. But I guess this works. Okay, so we have okay, so this is clear, right? So
Yeah.
And you also have that. Okay, so the main So the issue here is you're choosing a basis. So maybe you can augment it with something else. Oh, I see. I see. Okay, but this is. All right, but okay, so at least on this way you have this is the all ones vector is not in your space. Is that correct?
Yeah, they don't belong in my space.
Okay, I like this. So we're implicitly using something.
Like, does this work for like every K?
Yeah, this works for every K.
Can we just conclude that the dimension of like F infinity over U is like unbounded, and that's like infinite?
Yeah, so it's unbounded. The dimension is unbounded. Right, the dimension can't be anything less. The dimension can't be any fixed K.
Yeah.
Yeah. Yeah, so the definition of a finite dimensional vector space is if it has a finite dimension, if some finite dimensional list of vectors can span it.
Yeah, and by this like construction show that they cannot be covered in finite kind of thing.
Right, that's a good question. I'm sure there's a simple proof of this. Yeah. Yeah, so this is exercise. The conundrum we are with is exercise 17 in 2B. Is it 2B? 2A.
Oh, I see. It's oh, wait, couldn't we just oh,
Yeah, you could cite that, for at least for your homework. If it's the question verbatim on the test, then you have to prove it. So this is enough. It's enough to come up with. It's enough to come up with one that is not. Yeah, it's sufficient to come up with for any k to come up with a list of k independent vectors. That's what 17 says. So, and then that's exactly what you did.
yeah.
Actually, I think that there's no, here is, I think you can do this instead to make it easier. I don't think you need the prime. You could just say J is a multiple of I.
Oh, I try to use the I prime so that I try to avoid them sometimes that the coordinate can be shared.
Oh, right. Yeah, okay.
It makes the proving that they are all nearly independent way easier.
Yeah, I agree. In fact, this may not be true. Oh, yeah, okay, I agree. I think this is true, but I like your thinking. So let's stick with that. Couldn't you just say a power of I? Does it have to be a prime?
Yeah, I want it to be a prime so it can avoid like having shared coordinates. Just power of I would be like if you try like power of 2, then it may intersect with power of 4.
Oh, right, okay.
Yeah, I got inspired from
Okay, yeah, okay. All right.
oh, for the exercise 17, in order to do that, I would try, yeah.
So now the question is, why is 2A17 true?
In my case, I try to prove by contradiction and induction. Like, let's see.
All right, so how do you do 2A17?
The other one. Oh, I just put my contradiction. Then if B is finite dimensional, then I would mm, assume that there's like B1 to the n is the basis of B, and I would its basis is like too strong, but like then if I try to pick the B n plus 1, then it must be contained in the span of B1 to the n, and that would be contradict as I want like B1 to the plus 1. If then if that's the one way. Oh, you want that one?
Okay, so one way straightforward.
I can't remember the idea, but it's hard to describe it. It's linearly. I think we should start with like the assumption that U is like infinite dimensional, but also there, like for every k there exists one to be k is linearly independent. So I think have like
The key thing's the definition.
I think wait the definition again. Oh, oh my god. A vector space is infinite dimensional and it's not infinite dimension. How's that gonna work?
Oh, now you just apply induction.
Oh. Oh yeah. If it works for k, then we know that works for k plus yeah, it's like an algorithm, and then we repeat that to like k, and then for k plus 1. Yeah. I wrote my answer again on these. I'll translate it back.
All right, so there's the proof of that.
Yes. And from the result of that, we can say that like the dimension of the if the dimension of B is larger than any arbitrary k, is it already infinite dimension? Right.
Say that again?
So from the result of this, can we just say that like if the dimension of B is larger than any k, then that means that it's infinite dimensional.
Correct.
Oh, so that works. It's just that.
Yeah.
Oh, so I was missing this proof. I guess I have the idea from the time, but then I don't know if it's.
You did the hard part.
Yeah. I just feel like it wasn't like strict enough to be a formal proof, because it's just from my intuition that I try to avoid explaining like intersection and then feel that they are like linearly independent. But like it's just my feeling that if I have like a linearly independent set for any length, then it will be infinite dimension. And yeah, I forgot about this result too. So like every in the test, do we have to like? Is there a limit on any? How to ask, but like I don't know whether which theorem we can use without proof and which one we have to prove before you. Is there like a limitation to that?
I think it will be very evident.
Like anything that that is mentioned in Axler, like in the textbook, not the exercise, is ready to use, right? Or are they? Like, let me see. I find some theorem. It's very useful, but I find like the for any like finite dimension of for any being vector space that is finite dimensional to like there's one in Axler that mentioned that it can be separated into like the direct sum of u plus w. So can we use that like straight away without proving?
Wait, this is
It's too
there's
much.
there's something else about U and W.
Oh, they are all subspace of B. Oh, it's like given the subspace U and there exists a W W so that it has following.
Yeah. So unless you're asked to prove that, I mean, some of these things are just foundational. So I would say you can use them. I don't have like a hard and fast rule for this. I think the best philosophy is the exam is a demonstration of your knowledge, and by using a powerful theorem, you're demonstrating your knowledge.
Yeah.
Does that make sense?
Yes.
Yeah. And then you have to be a judge if the demonstration of your knowledge is just saying the problem again, then you're not demonstrating knowledge.
Yeah, that makes sense.
So and of course this is a continuum. So you have to be careful. But I think by and large it should be clear, even if it's not explicit.
Mhm. I guess that's all my questions for today.
Anyone else?
I guess I'm leaving. Goodbye.
All right, goodbye. Anyone else? Or are you guys hanging on? That might be a problem.